So this video is primarily on breaking vectors into components and then resolving components back into a vector. And even just talk about how do we handle two-dimensional vectors. And a lot of times before we've had one-dimensional vectors, and we could talk about directions as just being left and right, so plus and minus work just fine. But if I want to identify a spot on this Cartesian coordinate system, and a Cartesian coordinate system is just two axes, one that's set 90 degrees to the opposite one or to the other one. So this forms a 90-degree angle in here. And the way that we're going to describe the direction of vectors along a two-dimensional space is to look at the angle that is formed. We could use that. With the positive x-axis going counterclockwise like this. So if I want to identify the direction of this vector, I'm going to use this angle theta. And I've actually written out this vector in terms of its length. So this is the magnitude. And the direction is given by an angle here. So this angle is about 49.4 degrees with the positive x-axis. So we have magnitude and direction, which is all we need to distinguish a vector. And this could be anything. There's no units here, but it could be a position vector. Maybe these are almost like longitude and latitude lines to identify a spot on a map. So we could say that this location right here is 9.2 units away from the origin and makes an angle of 49.4 degrees with this positive x-axis. So this could even be something like east, north, west, and south if it were a map. Now, this could be a map of some island that looks very much like an amoeba, and you wanted to locate some specific location on the map and tell everybody where the buried treasure was hidden, and so this is one way to do that. Another way that we can take a look at a vector in two space here is to talk about it in terms of its x and y components, which is to say we need two things to identify this vector. We did a length and a direction with an angle here, but we can also identify this spot by taking a look at the grid that I placed on top of here. So if I take a look at the grid, to get to this spot, I could go over 1, 2, 3, 4, 5, 6 to here, and then I could go up 1, 2, 3, 4, 5, 6, 7 to here. And if I draw two arrows to show that, it would be one arrow pointing straight to the right, and then one arrow pointing straight up. This one has a magnitude of 6. 1, 2, 3, 4, 5, 6. This one has a magnitude of 7. And these are called components of vector B. And we write them as Bx and By. They also get arrow hats because they are vectors. I drew them with arrows here. They have direction. Now these are one-dimensional vectors. Bx only exists horizontally. By only exists vertically. So for the directions of the components, we can just use plus or minus. These are both pointing in positive directions. So the directions of vector Bx is positive 6, and then By is positive 7. You don't need to write the positive, but I'm writing it just to emphasize that there's a direction to these vectors. Because there's a grid, you could actually count the 6 and the 7, but what if you wanted to find these lengths and you didn't have a grid? Because you're not going to have grids on problems. So what we could do, and I'm going to erase this stuff here, we could also find the components of B by using right triangle trig. The two components, Bx and By, they add together tip to tail to give you vector B. The tip to tail for this particular case, because these are components in the x and the y direction, ends up in a right triangle. Bx and by make a right angle to one another. So we could use right triangle trig to find these. The x and y components can be found using sines and cosines. I found the easiest way to break a vector into components is to first just write down the magnitude of the vector you're breaking up for each one of these. We're breaking up a vector that's 9.2 units long, so I'm going to write 9.2 after each of these. Now one of these is going to get a sine term because we have to break this angle into sine and cosine parts. The one that gets the sine term is the one that's opposite the angle. The component that gets the cosine term is the one that helps make up the angle, or the adjacent part. So this part helps make our angle. It's the x component, so I'm just going to write cosine here. The other part gets the sine. And then the angle that I'm using to make my triangle, 49.4 degrees and 49.4 degrees. And if you put these in your calculator, you'll see, along with rounding, if you round to significant figures, that 9.2 cosine 49.4 is going to give you 6, and then 9.2 sine 49.4 will give you 7. So this is how we can calculate the x and y components of a vector that we want to break up. Before I go on to the next slide, let me also show you a PhET app. This is from the website, the PhET website at Colorado. And you can find this if you just Google search PhET. It's kind of down here. It's probably the first thing that's going to pop up. And this is one of the apps that allows you, and you've probably seen this in class, but allows you to take a vector. I'm going to grab one from the barrel here, and I'm just going to put it down, and I can grab the tip, and I could change the length of the vector, and I could change the direction it points. And as I do that, you'll see here the angle that the vector makes with a positive x-axis is given. So this is the direction of this vector. If it points straight to the right, well, close to straight to the right, we get 0 degrees. And r, which is the length of this vector, r with the absolute value sign. Absolute value signs in vectors mean the length of. Is 25 apparently for this vector. And as I change the direction it points, you'll see the angle keeps getting greater and greater. Straight upwards will be 90 degrees. As I go over this way, we'll get all the way to 180 degrees on this side. Now it says negative 180 because another way to talk about the direction of a vector is to go clockwise from the positive x-axis and then just use negative angles. But I'm just going to use counterclockwise positive angles for all of my demonstrations. Another nice thing about this simulation is that you can put a vector down, and I'm going to go ahead and attach it to the origin. Not that we have to, but just to show you what the components look like. There's something called component display. So you can look at the components of this vector. They kind of come up as these pink-looking arrows. And you can see the components change. As I make the vector longer in the x direction, the x component gets longer, but the y component remains unchanged. Over here, they calculate the x and y components for you, and they keep updating as you move around this vector. So if you need to get a sense for what components are, they're telling you how much this vector points in the x direction and y direction exclusively. You can go to style 2 here, and it will show you the components, same components, but it organizes them tip to tail. So you can see how the components are always adding tip to tail, even in the negative region down here. Style number 3 adds lines on here, so you can kind of see the rectangle made by the components and the vector itself. So we'll go back to that in a second. I want to show you on the next slide another example of breaking a vector into components, but this time I also want to have a negative component just to show you what that looks like. So this vector has a length of 9.8. It could be anything. Maybe if it's a position, it could be units of meters. I just left the units off, so it's a purely mathematical vector. 206 degrees is this angle. Doesn't seem terribly useful. And actually, the best thing that you could probably do in this case is figure out what the small angle is. If I draw in components for this vector, the components of this vector, the x component is going to point off to the left. do this in red. The x component is going to point off to the left about this far, and the y component is going to point down about this far. So this would be c sub x, and this would be c sub y. And you'll notice the right triangles formed right here. So while you're given this 206-degree angle, the angle that makes the most sense to take a look at is this one right here. So let's find that angle. That angle is going to be, well, if it's 206, we know that from here to here is 180 degrees. So 206 minus 180 should give us this smaller angle that'll be a little bit easier to work with. And that comes out to 26 degrees. So we're going to use this 26-degree angle. And again, the fast way to break a vector into components, I'm just going to write out cx and cy. Realize that the components are part of the whole vector. So each component gets the magnitude of 9.8. But then we're going to break it into parts using sine and cosine. Which one gets the sine and which one gets the cosine? The component that helps make up the angle always gets the cosine. It's the adjacent side. So in this case, it happens to be x. It doesn't always have to be. If we use this angle over here, then the component that helps make up this angle would be the y part. But in this case, it's the x. So I'll write cosine here. I'll write sine here. And then the angle that I'm using, 26 degrees, 26 degrees. And when you do the math on this, you'll end up getting, hopefully, what you see here on the grid. That's cx and cy. Let's see, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9 to the left. So when you just do the math for this, you'll get 9. The direction you can see by the picture, it's pointing to the left for cx. So this has to be negative 9. 9 to the left for the x component. The negative doesn't come from the math. If you do this method of finding this angle, you're going to end up putting the negative sign in because of a picture that you drew. Y component likewise points downward. 1, 2, 3, 4. So the y component should be negative 4. So now we broke this vector into components. And lastly, what if we wish to take two components and resolve them into a vector? So here I drew components that I'm calling ax and ay. So here's ax. It's pointing to the right 5. And here I actually put units on it, saying, what if these were components of a velocity? The x component is 5 meters per second to the right. The y component of vector a is negative 8 meters per second. So that's 8 meters per second downward. And I drew them on the grid, 5 over and 8 down. We could take a look at what the resultant vector would look like. In fact, it might be easier to see if I take vector ay and I drag it over here so that it's tip to tailed with ax. Because then we can see the resultant vector as being a vector that should start here at the beginning of the chain, point over here to the end of the chain, and I'll try to draw it in, although it won't be terribly neat, but it should be a vector that looks something like this. That would be vector A. And vector A is equal to the addition of these two vector components, ax plus ay. We can see by tipping the tailing that that must be true. So how are we going to find out the length and magnitude of vector A? In other words, I'd like to find out vector A in terms of its magnitude, and then an angle sign, and then its direction. Kind of like how we showed the first vector in the sequence over here. I'd like the magnitude, and I'd like the direction in terms of an angle. For the record, that is called a polar notation for vectors. So the angle that I'm going to try to find, I suppose, is this really big one over here. But let's not find that one yet. Let's just use our right triangle, and let's find this angle theta right here. Because it's an angle within our right triangle that'll be a lot easier to find. So we know the sides of this right triangle, so we could find the magnitude of A using the Pythagorean theorem. We could say that the magnitude of A is going to be equal to the square root of ax squared plus ay squared. So that's going to be equal to 5 squared, the square root of 5 squared, plus negative 8 squared. The negative is just going to go away anyway, so I'm just going to write 8 squared. And if we do that up in the calculator, 8 squared is 64. Add 5 squared to that. 5 squared is 25. So we're going to get the square root of 89, which is about 9.43. So this vector has a length of about 9.4. I happen to have units on these, so this number isn't just a number, it represents a velocity, 9.4 meters per second. Then what angle is this over here as well? The angle, I'm going to use a little bit thicker for the angle here. The angle here we could find because of the relationship between ay and ax in terms of the tangent function. Remember that the tangent of theta is going to be equal to the opposite side over the adjacent side, which in the context of this problem means that it's equal to the y component divided by the x component length. So I'll have tan theta is equal to the y part, which is 8 downward, but again this is a right triangle, I'm just going to use the length. So 8 divided by the adjacent side of 5. So I get the tangent of theta is equal to 8 over 5, which is 1.6. Now this hasn't gotten the angle yet. We just happen to know that the tangent of the angle is 1.6. To get theta by itself, remember tangent is a function. This isn't tangent times theta. To undo a function, you have to apply its inverse function. So we'll apply inverse tangent to both sides of this equation here. Inverse tangent of the tangent of theta on the left side, and then inverse tangent of 1.6 on the right side. Now the inverse tangent of tangent just undoes the tangent function. It leaves us with just theta on the left side, so we have theta alone. That equals the inverse tan of 1.6. So the angle over here is going to be equal to inverse tangent of 1.6, which you can do in your calculator, but make sure that you're in degree mode. That ends up being 57.9 degrees, or right about 58 degrees. Now that's this angle here. What I technically want for my vector is this large angle here. So the whole thing all the way around is 360 degrees. So I'll get this leftover part here by doing 360 minus 58. And 360 minus 58 is 302. So vector A is 9.4 meters per second at an angle of 302 degrees.